about the scope of things that I think will be of interest to a large number of you. What I want to do is maybe first, actually, before we dig into the slides, let me show you the outline for today. So effectively, we try to maybe peel away some of the layers of the onion and show you from the big picture down to some of the details. So as we go, we're going to get further and further into programming concepts and computer software architecture. But to begin with, I want to lead you through some of the background, and then Csaba going to talk about some of the overall functionality of the software. And then I'll take down one more level, and we'll talk about some of the background and the motivations for what led us to make certain decisions. Then we're going to give everybody a little break, stretch our legs, and then we're going to dig into what the architecture allows you to do. And then finally, we'll try to introduce you to some of the programming concepts and be sure to give you links to additional information that you can build on. And hopefully this will be the opportunity to kind of kickstart people's thought processes and really hopefully open your eyes to some of the things that are possible, and we look forward to working with you on them. So let's dig in then. I hope everyone can hear me okay. Feel free to interrupt with questions or any comments that people want to make, especially if you have trouble with any of the translation. I'm happy to, don't speak French very well, but I can speak more slowly maybe if that helps. So what is Slicer in the big picture? It's really just a desktop computer software application. It runs on multiple operating systems. It's been in the works for quite some time now, since probably the early 2000s. And, since we started really officially keeping track with a release in 2011, there have been about 750,000 downloads. So that's cumulative over multiple versions, but there's quite a bit of activity. It's a very active community. There's over 13,000 posts a year on our online forum, and also it's very important for research. It's been used in at least 11,000 publications, ranging from cancer research to fundamental biology and a bunch of other things that we'll talk about here in a little bit. So it got started, really as people were getting excited about the possibilities for computer graphics and medical imaging. Groups at Brigham and Women's Hospital, that's BWH, you may see that. That's in Boston. It's a Harvard-affiliated research institution hospital, and General Electric, where we had some really good colleagues. So Ron Kikinis, you'll hear his name quite a bit. I've tried in these slides to highlight some of the people involved. Ron Kikinis really pushed, he's a radiologist, but really a researcher and a visionary motivator to kind of encourage computer scientists to get involved in medical research. And so the key people who were involved early on, Dave Gehring did an MIT master's thesis on neurosurgery planning in 1999. He really put the core of the old Slicer, what we think of as Slicer 2K, into place. And then Delphine Nain and Lauren O'Donnell were very critical in furthering the whole infrastructure. And then finally, that was a good basis for some funding projects that a number of us have been involved in. And so really, you have to look back at all that and kind of use that as kind of the framework to understand that there were some key problems about how software needed to be organized and what kind of things the medical community expected. And that's been at the heart of Slicer development for quite some time. One of the other key pieces of Slicer's kind of recipe for success, if you will, is the software license that it uses. I'm not going to go into all the details of the legal side of it, but it's important to know that Slicer is a permissive license, in the sense that people can use it as the basis for medical computing products. So things that would go on the market under the FDA or the corresponding regulatory frameworks in different countries, can be built using Slicer components. Either use it all as is, or take bits and pieces. Anything is acceptable. And in fact, it's encouraged. It's one of the main reasons that we created the slicer package, is to create products that would help people, because if they're not made into products, they can't actually be used by doctors in routine cases. I think one other fine point that people who are who are computer scientists may appreciate more of the details, or lawyers might appreciate, is that there are no reciprocal licenses, no viral licenses in Slicer. We're very careful, and we'll talk about this more, to not build on code that requires re-release of your code, and that is essential really for the commercial applications in actual devices. So fast forwarding for about 20 years now, we have the current slicer, which is really very robust, I have to say, thanks quite a bit to the engineering talents of people like Chaba, who you'll hear from, and our colleagues. There's a lot of code, and it is quite a bit to learn. So we'll hopefully be introducing you incrementally to the bits and pieces of it as we go along today. But it's built on some very, very powerful component libraries, and it is, for a product of this scope, it is very, relatively well documented, and it is at least, quite feasible. We have lots of people who have learned to do really amazing things with it, and we'll try to illustrate to you that even though it is a lot of detail to figure out, it's also, a very achievable task, and we really are looking forward to having more people learn about it and get really good at developing, because there's a large unmet need for custom slicer development. Slicer is used in quite a bit in clinical research. So here's a sort of a fast motion view through one application that's been developed quite extensively at Brigham and Women's Hospital. This is for those who may not recognize it, those are MRI scans of a prostate, and this is actually showing you the registration of the images between pre-procedure and intra-procedural prostate MRI. This is part of a tool that's used for guiding biopsies to suspicious locations within the prostate. You can see in this series of images that there's a guide that is mounted to the patient effectively, and that's used to guide needles into the appropriate areas of the prostate under MRI guidance. And this has all been done. It's a specific example, the Slicer Prostate Slice Tracker, of how you can customize the Slicer infrastructure to accomplish very specific clinical goals. So one of the other things we'll talk about quite a bit today is the Python interface. So Python is, at this point, certainly one of the most popular computer languages in the world. It is a high-level language that manages a lot of details about platform abstraction and memory management and object-oriented constructs in a very accessible and powerful syntactical environment. And it comes, maybe the best thing about Python is that there are literally thousands and thousands of very useful software packages to use. I've listed a few here. So one of the concepts it's going to come clear as we show more and more examples today, is that Slicer has a huge suite of things that are available to you in Python that can be mixed and matched in a multitude of ways to accomplish things that might, without the Python wrapping, they would probably still be possible, but they would be immensely more difficult. So rapid customization, experimentation, debugging, customization, that's really for the purposes of probably 80% of what people do in the Slicer environment. You can do it in Python, and you probably should if you have the unless there's some specific barrier. And we might talk about some of the reasons why you would use C++ instead of Python, or even other custom languages. But primarily, we're going to focus, at least today, on Python. Then the other concept to remember is that Slicer is built on this concept of extensions. So I'm showing you here a little video of the Slicer Extension Manager. These are some of the things that are available. Effectively, these are like an app store for add-ons to Slicer. There's 100 plus of those available. They range from kind of utilities, developer utilities, but some of them are quite developed, maybe specialties, if you will. So craniomaxillofacial surgery, radiation therapy, prostate imaging. These are all areas of specialty domain that that can be customized. So your Slicer environment really is more suited to the particular kind of research or the kind of work you're trying to accomplish. We'll talk a little bit about this. This is just another example of something you can do with Slicer. Is it can drive virtual reality equipment, so it supports many off-the-shelf commodity tools. And one of the things that we like about this is that it is implemented in such a way that there's nothing really too custom about the Slicer applications. They use the same coding environment that you would use to do regular interactive computer graphics with a mouse and keyboard, but you have now the extra dimensions of head motion and multiple 6 degree of freedom controllers. And, that has opened up a lot of interest and a lot of opportunity for people who are looking at customizing things. Another feature that we're finding increasingly interesting is the ability to leverage remote rendering, which often is done using some cloud computing resources. So this is an example of a very large data set being rendered on a remote server. This is a data set that consists of 1700 by 1700 by 1200 floating point voxels, which is, I think, beyond the scope of most people's computers or laptops. This one is actually running on an Amazon machine with a V100 NVIDIA GPU. But if you look at the frame, you can see that it's actually it's being viewed in a web browser. So we have a remote desktop access to this large data set. And increasingly, we're seeing large data sets, not just from clinical domains, but also from research domains like microscopy and ex vivo imaging for a variety of purposes. And so Slicer's turning out to be well suited for that kind of application as well. And then finally, there are a few other use cases. I won't really go into these, but the opportunity to mix and match. You may have heard of Docker containers. You may use them in your work. Slicer can be run inside a Docker container. Slicer also is beginning to be better integrated with web concepts. So if you have a hybrid solution where some parts of your work make use of a web page and other parts make use of desktop, that's all quite feasible inside making use of some of the same Slicer workflows. So I just want to close with a few thoughts. So technically, I think you'll find that Slicer has quite a bit to offer in terms of flexibility. Also, the licensing, remember, means there are very few constraints on how you can use it. The fact that it's an active community means that it's been ported and used in a variety of different operating systems. It's pretty robust against a lot of things, and it also is compatible with the latest developments, so deep learning libraries and computer vision and user interface and so forth. So that amount of effort you get to leverage, and you get to invest your time in learning something that's going to be there for you, in the long term. You're not. It's very unlikely that Slicer is going to go away anytime soon, meaning that you can rely on it to be a platform to build on. But beyond that, I think it's also it's very gratifying to think, on the right here on the social benefits, right? We don't really have anyone who's a special owner of Slicer. Really, the only way to become an owner is to invest your mental energy and get to know it well. And once you have learned how to do work in Slicer and contribute to it, we're incredibly fortunate to have people who really put a lot of their effort into it, and I think we all benefit from that. And you know, I think it's also good that the Slicer effort promotes interoperability and open standards, because that helps in immeasurable ways. But I think those last bullet point on the right is kind of the key thing, is really what is science? Science is about making reproducible advances available to, you know, ourselves and our colleagues. And, you know, often nowadays I tend to question any publication or any claim, scientific claim, that doesn't come with this end-to-end open source reproducible implementation, because, you know, the essence of science is around that kind of publication. So we think this is the right thing for the community. We also think it's practically the most useful way to develop, you know, interesting projects that are useful to people. So that's the first phase of today. And so I hope that all made sense. I don't know if we have time for questions at this point. I think we're, you know, maybe got started a bit late, but probably I ran along too. Do we have any questions, or Jabo's joined at this point? Should we hand over to him?
I'm here.
Hey, there he is. Okay. Let me turn off my screen share then.
So if anybody has questions, feel free to ask in the chat or anything. We will try to answer them even as we go, if you would like.
Yeah, Saba, sorry. Usually when people have questions, they type it in the chat window.
That works.
Okay.
All right. So my name is Csaba Pintér. I am the Chief Technical Officer of two companies, one with Juan Ruiz Arzola. And I will talk about some end-user functionality of Slicer. So now, at this point, you are familiar with what is Slicer, where does it come from, and what you can expect from it as the big picture. But now I would like to present a little bit more about what are the basic things that you can do with it, in case you are not already familiar. So, of course, you need to be able to use your data. So you need to be able to import and export it. Slicer supports a wide range of different types of data sets. The biggest relevance today is DICOM, which is the standard medical format that basically every CT and MRI machine outputs nowadays. And it is a great vehicle to do your reports and segmentations and registrations, etc. Slicer supports a really wide range of DICOM data, ranging from these images that I mentioned through diffusion MRI, segmentations, radiation therapy data sets, etc. It also supports a bunch of research formats, such as NRRB, MetaIO, BTK. The advantage of these data types is that they can store 3D data in a way that DICOM does, with their actual location and geometry in space. But if you have your data as a series of JPEG or TIFF or PNG files, Slicer can also read them as a stack. In that case, of course, you will lose the spatial relationship. And Slicer can save and restore the state of the application as you see it. We call it the Slicer scene, and it can be done in a so-called medical reality bundle. On the right side, you see just a tree of data sets, so you can see that it's pretty colorful. There are different data types that we can use. So just a little bit more about data types. So the typical workflow in Slicer, when I say typical, is if you look at this course, maybe 80% of the people are interested in this kind of workflow, is that you load some kind of 3D image, as I mentioned, from DICOM, RRP, or something like that. You will want to visualize it in 2D and 3D. You will want to optimize this visualization, and then you will want to define some structures. We call this definition or localization or contouring, we call it segmentation in Slicer. And so it will result in a segmentation type object. And depending on what you want to do with it, for example, the very popular deep learning groups nowadays are looking for label maps, so pixel-based images that they can process. For nice 3D visualization, you can convert them to models. Of course, you will want to do some quantification, and then you can make some statistics, and which you can export to tables. So everything is pretty standard, and today's slicer supports this kind of workflow pretty nicely. So as I said, the first thing after loading that you want to do with your volume is visualize it. You can show your volume in 2D or 3D. You can configure how the layout looks. You can show multiple types of images in the same viewer. You can even show data that are not conventional for visualization, like transforms. In this little box labeled 4, you can see a deformation field as a warped grid in 3D. You can visualize surfaces and volumes in 3D as well. So for example, in number 5, you can see fiber tracts of the brain. And finally, you can show time sequence data or higher dimensionality data. So what you can see in picture number 6 is a volume rendering of a beating heart, which...
Hey, Csaba, sorry
yes.
to interrupt. I'm still seeing your title slide for some reason.
Really?
Yeah.
Still maybe it's just a matter, yes, now it's changing, of the window you were sharing. Yeah.
Interesting. I'm sorry. I just pulled it to the other monitor. Maybe it got confused. Okay.
Yeah. Sorry.
Okay.
That's great. Thank you. No, it looks great.
Thank you for letting me know. Otherwise, I would have said this and that image without.
Well, actually, it made to me at least it made a lot of sense without the pictures. So that's a good sign.
Yeah. Okay. So onto some less boring slides. So these are the data types. So it was okay without lots of images, and yeah, the typical data types, which is yeah. Let's just give you some time to see this picture, because I think it is pretty important. So you have your images that you load, and maybe I can show my cursor in some way. Can you see my cursor? Not really, right?
Yes, we can.
Yes, we do.
Can?
Yeah.
All right. So the 2D images that you can show in 3D, then you can do segmentation. It's a pretty complex data set. You can convert it to different other data sets that can be used for different ways, as I said, deep learning or some image processing or visualization, and then you can have tables. And the next slide that I had is about visualization. So you have you can show different types of data in 2D and 3D, and you can show them together or with different kinds of settings. As you see, for example, in number 1, it is semi-transparent. The transformed grid that I mentioned here, number 4, is the output of image registration that I'm going to talk about, and the 4D data, the beating heart, is a very convincing example of 3D slicer capabilities in terms of visualization. So very basics, you can show 2D slices, and then you can show them in the 3D view as well. So this is what you basically see when you open an image. You can show the same image in a so-called volume rendering when technique called raycasting is applied to visualize the internals of this huge pixelated image data that you loaded. As what you can see in this video is a cardiac CT that I just changed the volume rendering settings of. So I'm dragging this shift slider, and I can see the muscles and more the internals of the person. This is really nice for visualization, but unfortunately it cannot be used for quantification, which is a source of misunderstandings sometimes, as you can see in the Slicer forum. What you can also show in 3D pretty nicely are so-called models. These models are surface data that consist of triangles, but basically what you end up seeing is a smooth surface. What I have loaded here is an abdominal data atlas, and as you can see, I can clip the whole data set with a plane, so you can customize the visualization of these models as well. A very typical operation that you will want to do in 3D Slicer and in any medical workflow is registration. Registration means to bring two different data sets to the same geometry, the same frame of reference. It can be two images, it can be an image and a model, it can be two models, it can be a set of landmarks to an image, it can be many things. You can do it manually, which basically means that you transform the image with the mouse and keyboard and try to see in the views which is the best fit. Of course, it is not optimal to do that. You can do it semi-automatically. The most prominent way of doing it is landmark-based. It means that you place points in one of the views. For one data set, you set, the same set of points for the other data set, and then an algorithm calculates the optimal transformation between these two point clouds. And you can do automatic registration in 3D Slicer. There are many ways of doing it in the Slicer ecosystem. So, for example, this image on the bottom left shows the result of an MRI image registration. On the left side, they are not registered. On the right side, they are registered. The importance of deformable registration is that, for example, if you have the same patient coming in twice, they have different anatomy because they may have lost weight, the content of the bowels may be different, any other factors can happen, different position of imaging, etc. But you want to see the internals the same way because of the repeated intervention that you want to do on that person. You want to quantify it on the same frame of reference. On the right side, what you can see is surface or segmentation-based registration. This example is prostate brachytherapy when you do the planning imaging on MRI, which allows you to segment various structures, not just the prostate, but also the urethra and the tumor. But the imaging at the time of intervention happens on ultrasound, but on ultrasound, the visibility is much less optimal. So you want to use the MRI segmentation on the ultrasound image. So this automatic method, as you can see in a GIF, showing the different phases of registration, overlays the two data types together, and then you can do your brachytherapy needle insertion with the exact structures shown in their accurate place. So another important feature set in Slicer are sequences. As I mentioned, we can do time series and higher dimensional data sets. So these are just three examples. The top left is a recorded needle insertion in ultrasound. It looks like a phantom to me. Basically, you can record a series of these images, the location of the images, and the location of the needle at the same time points in a sequence, and then you can replay it, and then you can evaluate it. On the right side, you can see the beating heart example that I showed before, and on the bottom you can see some shape matching series, or it may be a series of imaging. I'm actually not sure about that one. So let's go to one of the major feature sets of 3D slicer that got lots of attention in the last few years, and it got a complete revamp as well. So segmentation is also known as contouring, and the goal of it is to delineate localize the structures of interest. You can do it slice by slice, and as I said, with image registration, you can do it automatically or semi-automatically. And this is used in basically all kinds of medical imaging workflows, surgical and radiation therapy planning, navigation, volume or shape analysis, interventions, and education as well. So this is, for example, an example of segmentation for 3D printing. We segmented the spine on a CT image. We added a base plate. We 3D printed it. We filled it with gelatin, and it's ready for training sessions with ultrasound guided needle insertions. Difficulty with segmentations and what people sometimes have a hard time understanding is that there are various ways to represent segmentation data. These are just four different ways. Label map is the most prevalent and surface-based, but there are other less typical types, but each of them needs to be considered, for example, because the type A is what you see in a radiation therapy plan. So you need to be able to go from one to the other. And what you can, the tool that you can use in 3D Slicer is called Segment Editor. This is a video that I made fast for easier congestion is the hard segmentation, where you basically just paint the insides and outsides of the structures that you want. And now you have an initial segmentation. You see where you have some inaccuracies. You do some corrections on the borders, and when you're satisfied, then you can do some different kinds of segmentation, for example, for the pericardium. And at the end, you have a pretty accurate hard segmentation. This took less than 10 minutes altogether. Yes, one more feature set that I'd like to mention is markups and annotations. It sounds pretty basic, but under the hood, it's quite complex. You can put down points, as I mentioned, with landmark registration. You can draw lines and measure distances. You can measure angles. You can do curves, open curves and closed curves. You can also measure their lengths and now also the curvature. You can place planes. You can visualize the 3D relations of these objects in the 2D plane. So for example, with the plane, you can see where it intersects and which one is behind and in front of the axial slice. And you can have box regions of interest. So of course, there are more than 100 modules in 3D Slicer, and there is no time to describe them all. But these are, I think, the major feature sets of Slicer. And if you want to know more, you can look at the documentation, obviously, and ask us. And I just want to show two pictures from the last years. One is in South Africa, featuring 3D Slicer. And so this was the second section. Thank you for your attention, and the floor is again Steve's.
Hey, thank you, Csaba. Well, I hope that was illustrative of the scope of things that we're talking about, and we're going to take another level of another layer of the onion off and dig in a bit more to some of the programming aspects of this. So I want to switch now to sort of from a functionality point of view to more of an introduction to the programming part of things. And I hope the slides come across well. So this first slide is kind of the agenda for this section, the topics I want to talk about. And they are, while we're not going to really be showing any code here. I'm going to be talking about kind of the architectural concepts or the key motivators that drove some of the decision making behind the implementation of Slicer. So this, I already mentioned this, and I want to reiterate that the license was kind of not exactly the very first thing. We kind of, at the time, we didn't really, when we first started with Slicer, we kind of didn't define what the license was going to be. The group kind of like, like a lot of software packages didn't say what it was, but we ended up getting this grant, this multi-institution grant called NAMIC, and it stood for the National Alliance for Medical Image Computing, which had like 15 different universities involved. And so one of the very first things we wanted to do was kind of define the rules of the road for how all those groups would work together. And some of the groups that were involved were actually commercial groups. Chaba and I, as has been mentioned, both do commercial software development and build our work on Slicer. And we wanted to ensure that that was going to be possible to do. And so we defined basically Ron Kikinis and I and a couple of the lawyers from the Brigham Institution got together and really kind of laid out what we thought was important. And so some of the things I mentioned, like non-viral, no GPL code, if you're familiar with that term, but also we wanted to make sure that we didn't get any patent trolling. And that's maybe kind of a slang term for a legal tactic where there's a so-called submarine patent concept, which is where some open source software in the past has been made available under a free license, but the free license didn't include a free license to the patents. And people, they're called submarine patents because after people come to rely on it, all of a sudden it comes to the surface, and people have been subject to legal headaches because of that. And so one of the things that the Slicer license says is if someone contributes code to Slicer, they not only give license to the code, but they also agree that if they have any patents over the concepts behind it, they also grant a license to that. And that's one of the things that's incorporated in the Slicer license that isn't available in some of the shorter licenses, but we felt it was important for our purposes. Also, one of the things the Slicer license says very explicitly is that this software is intended for research and that clinical use is entirely the user's responsibility. And that was another sort of subtle legal thing that the hospital lawyers thought was very important that we settle on, because they didn't want to make it sound like they were offering clinical software and encouraging people to use it on their patients. But at the same time, they didn't want to prevent that. And so the software is, as we make it available, intended for research, and we intend you to use it for research. That means following ethical review boards. It means being aware that the software is not FDA approved. It's not a product. No one is making claims about its effectiveness other than its use in research. And yet, at the same time, we want to make it clear that you can do anything you want, and it's consistent with regulations that are in effect where you are, but it's all entirely your responsibility to make those decisions. And I hope that's a fair and acceptable way for people to interact with the software and the community. So the consequence of that is that because we want Slicer to be free and available in the way I just said, we need to build our software on top of other pieces that are also similarly free and non-restrictive. So there's an entire course, I'm sure, possible about the concepts behind different software licensing terms and how they play out, especially in different countries and different jurisdictions. But we hope that we've covered our bases very well. Fortunately, we were able to build a complicated package like Chaba just showed you on top of a wide range of open source tools. And we're very careful in selecting those tools to make sure they don't introduce additional restrictions on our end users or our own use. And similarly, we're very open about our process. It's very transparent. All the code necessary to build Slicer is available in public repositories. Also, the issue tracker, as in bug reports and feature requests and so forth, take place on the GitHub forum. The GitHub repository and the organization there. Then there's also a very lively discussion, as I mentioned, on discourse.slicer.org, which is our online forum, and everyone here is welcome to join and to join in that discussion. Hopefully it's fairly easy to read. I should say, in addition, I don't know how many folks here would be aware of it, there is also a discourse instance on slicer.cn. So it turns out that there is also, as you might expect, a very active clinical and developer community in China. So for probably obvious reasons of convenience, there's a Chinese language forum that tends to attract Chinese speakers. As far as I know, we don't have a corresponding French instance. That might be something to consider if it turns out that there are more francophone developers who might want to discuss in French, but as right now, Discourse is, at least for the majority of the developer community, the place we go, and it is in English mostly. Then we also have weekly developer video conferences. They're open to anyone as well. If you really decide to get into the details, or you just have like a one-off question, feel free to join those. And then this week is actually Project Week. Normally, we would be getting together in person. There have been, as Chava kind of mentioned there at the end, we've been in Las Palmas 3 times, I guess, for Project Weeks. And then those alternate between Europe and the US or North America. So we often have ones in the summer in Boston, and then during the wintertime in Las Palmas, which is great. So I think it's again a very open community, and a lot of the decision making is consensus, just it's a very technocratic meritocracy where people make their decisions based on what's kind of consistent with our overall best practice, we think. So I think it works out pretty well. So another thing consistent, in terms of guiding our choices from a programming point of view, are the building blocks to make sure that everything is cross-platform. So Chava showed you examples in Windows, but the same code runs the same on Mac and Linux, which is great because sometimes you may need, to mix and match between different tool sets in order to take advantage of different hardware capabilities or other special code maybe that's closed that you can only run on one platform. So here's a concept that may be, I don't know, simple and yet at the same time it is hard to pull off in practice. And I like the analogy when thinking about making things modular and reusable. It's funny to me that a lot of times when people talk about modularity, they'll use the metaphor of a jigsaw puzzle pieces fitting together, and somehow that seems to appeal to people to think, these fit together perfectly like jigsaw puzzle pieces. But if you think about it, jigsaw puzzle pieces only fit together one way, and they only make one picture, and so they're really the wrong metaphor for software. The better metaphor maybe is Lego bricks or construction equipment, because you can make all kinds of different things, and well-designed software, one brick shouldn't care whether it's part of a Star Wars scene, or if it's part of a kid's fairyland, or whatever it turns out to be. So the concepts in the slicer software are to make modules that are focused on what they do, but do not assume much about the outside world. And we'll probably touch more on that, and maybe when we get deeper into the software, some of this will make sense. I'll just mention here kind of the biggest picture building blocks. So the MRML, the medical reality markup language, you'll hear that maybe as if it were a real word, MRML, but it's just this concept of the in-memory representation of the scene, the current state of the software. And that includes the models, the volumes, the current state of the rendering. Everything about that is in memory for fast access, but it's also possible to save it to XML and reload it from XML. And so we call those files .mrml files. And then when you put an MRML file and all the data together into a zip file, we call that an MRB, or a medical reality bundle. So that's really just about data and describing the data. And then we use the term logic to describe manipulations of that data, transformations, algorithms, manipulations. And so those two pieces are purely invisible, let's say. They're just in memory and algorithms. But then the graphical user interface and the displayable managers, those are the parts that actually expose the MRML scene and the functionality to the user. So the user can see it, they can interact with it, they can manipulate it. And a lot of the pieces of the software, even though it's big and complex, follow this logic and follow this architecture so that, you know, once you kind of get your head around it, you know where to go to attach certain functionality or where to go to manipulate things. And hopefully by following this path, you'd be consistent with the way other developers think about the same problems. So another consideration that we're very interested in is efficiency. And I see we're going to run a little bit into the break here. I apologize, but I'll just keep going here and maybe speed up a bit. So we want to be able to deal with large data sets. As Csaba mentioned, they're not just large volumes, although sometimes they can be very large, like the brain image I showed you, but they can also be time series of volumes, like even video. So efficient use of memory is important, and we want to give people, you know, pointer level access to do manipulation. We want to be able to handle different data types, large data sets. Some of the memory, you know, some of the machines now, I mentioned you can rent computers from Amazon. You can get computers now with 3 terabytes of RAM or more, and that's all manageable. Slicer runs in that kind of an environment, and it's very important to us that we have access to that efficiency. And in the same way, we also want to have access to computational efficiency. So some of these newer platforms with hundreds of CPU cores and GPUs, in general, Slicer can make pretty good use of that. I mean, there's always more opportunity to customize, but at the image processing level, Slicer uses multi-threaded algorithms that divide volumes, for example, into slabs and process those in parallel in multiple threads. And then, of course, our data gets loaded in GPUs for efficient rendering using fragment shaders and vertex shaders and so forth. And then also we can, if the drivers are available on the platform you're on, you can access other kinds of hardware like GPU hardware for custom shading. And then another important consideration from the programming point of view is how can we cover all the elements that are necessary for medical imaging. So I think Csaba nicely summarized and gave you examples of these things. But it's important, you know, when writing the software like this to keep in mind that the kinds of real world data that you're going to be working with, and in medical applications, it's very important to know patient coordinate systems so that you can display right and left correctly, so that you can, you know, so many papers you see the heads are upside down because the programmers didn't really even know, you know, what they were looking at in order to correct for that. So Slicer, we're very particular about that. We do not want to get the coordinate systems wrong ever, because people like our surgical colleagues, you know, under research controls may be deciding where to place their scalpels based on where we put our markers on the skin. So it's really, really critical, and we're kind of picky about that. If anyone contributes code, we're going to not accept it if it doesn't pay careful attention to that that factor. We also want to, you know, in general, it's not our main focus usually, but it's actually good that Slicer is generalizable. So there are a couple projects that are pretty well developed regarding, for example, biological morphometry or even astronomy that make use of the same Slicer software infrastructure, but extend it in ways that are non-medical. So we don't really emphasize that as much because I think the majority of the community is medical, but the biologist community is getting pretty big, and I know there are some very dedicated astronomy users as well. And I think this is maybe the last of this, is that we really wanted the concept of Python scripting to be fundamental to the design of the program. Now, that's not to say that the core of Slicer is implemented that way, because most of the baseline functionality you'll find in C++, but and the main reason for that is we want it to be efficient, and C++ gives you a certain organizational constructs that are very useful, and we rely very much on C++ dependencies like BTK and ITK and CQT. But we also want to make sure that we expose all that in a way that allows you to be interactive and high level and efficient in implementing the customizations. And also we want to be compatible with other Python utilities. So the ability to pip install functionality is very important to us. So and what you'll see as we go through here is that there are kind of, I don't know, rituals or templates that you follow. And as long as you follow that sort of style, then you get a lot of this stuff automatically. So your code, by following that approach, can benefit from a lot of interoperability that turns out to be crucial for implementing complex work. So what you'll see later today, then we'll take a quick break, and then afterwards we'll come back and we'll start introducing some of the inner workings and give you examples of how to get variables that can refer to internal data sets, make function calls, define operations that operate on objects and classes, how to access some of the internals of your data through arrays and indexing, and how to do some sort of interesting control flow. We're not really going to talk about the C++, but I will say that if people have reasons to use C++, you'll still benefit a lot from learning the Python stuff first, because the API is basically the same, and it really is just a matter of convenience to work with Python. But if needed, the same concepts will translate. So that's it for this section. Let's go ahead and take maybe a shorter break. It is 3 minutes before. How about picking up the second part at 5 minutes after the hour? I guess that'll be 14:05. And that sounds good to people.
Okay, good. So let's take a break and we will be back in 8 minutes. Okay, at 5 minutes after the change of hour. Okay, thank you.
Thank you.
Hi everyone. I hope everybody had the chance to take their breaks. So if you are ready, then I will go to the next presentation, which is about 3D slicer extensions and solutions examples. So I'm not going to go into programming details this time, just show you what's out there, what are the things that can be achieved. And I will focus mainly on the image-guided therapy aspect, as that is the main focus of our common projects. So 3D Slicer has an extension manager, which can be described as an app store. It contains dozens and dozens, I don't know the exact number, but many extensions that you can just install by a single click. Each of these extensions contains at least one module. A module in 3D Slicer is a single-purpose piece of the program that has a little panel on the user interface and some functionality. For example, I showed you the segment editor in the previous presentation, or markups, and there are many others that you will see examples of. These extensions can be, as Steve mentioned, the same programming languages as the core of Slicer can be, so C++ or Python, and different combinations and variants of the exact structure. I'd like to mention here that Slicer is also used commercially, so there are a bunch of modules and extensions that are not released to the public. Here are just some of the companies that use Slicer internally or develop for other clients. So I would like to dwell into the extension, some of the extensions and solutions. The first one that I would like to highlight is Slicer IGT. IGT stands for Image Guided Therapy, and this ecosystem, so to say, contains tools for navigating medical interventions. So navigation means that you use images of the patient to guide therapy, for example, needle insertions. And nowadays it is routine in many hospitals and clinics around the world for anesthesia, biopsy, central venous catheterization, oncology, as I mentioned in the previous slides, brachytherapy, etc. And the takeaway of this type of this approach is that it reduces cost and the risk of the open surgeries by making it minimally invasive. I guess most of you already knew that, but let's just wanted to summarize quickly. So what does it look like in Slicer? So you have some modules that interface with devices, and you can see the spatial position and the image that these devices transmit to Slicer through an open protocol. And as my colleague Tamás shows you in the picture or in the video, he inserts a needle under ultrasound guidance, and he can see everything that happens on the Slicer window. So I just want to mention that ultrasound is the mostly used imaging modality in image-guided therapy because it is safe and portable and inexpensive. But the downsides are that the image quality is not as high contrast as in some others like CT and MRI. Simultaneous manipulation can be difficult. You see that he uses both hands, and it requires pretty fine motor control. Or and of course, transducer may just block the ideal needle path. So you see that he's inserting the needle very close to the ultrasound probe. So this kind of intervention also needs pretty extensive training as well. So as I said, many devices are supported, which is done by a toolkit that runs under the hood of Slicer IGT. And you can use a really wide range of ultrasound devices, video capture devices, robots, position tracking tools, etc., using the same kind of interface without having to worry about the type of device in the application. So you put together your hardware system, edit a configuration file. I will show you an example in the last session, and you can use the Slicer IGT tools in the very same way. So just a few examples of early Slicer IGT usage. In orthopedic surgery, you registered the spine to the reference marker in the position tracking system. And then under this guidance, by seeing the segmented CT, you could plan and insert the screws exactly the same way as you could insert this exactly the same way as you planned, and planning can be really accurate with the tools provided by Slicer. So you can see the planning in blue and the insertion in red. You can also do scoliosis monitoring under ultrasound guidance, which is important because monitoring scoliosis usually happens under fluoroscopy, which is ionizing radiation, so potentially harmful for children and of course adults, but scoliosis monitoring happens mostly on young adults and children. So the takeaway of this is that you can reconstruct the spine using only ultrasound under tracking with Slicer IGT, so saving the some of the risks of this detection. Of course, other minimally invasive techniques can be also used under Slicer IGT navigation. For example, thread ultrasound guided nephrostomy. You can see that the clinician is finding two planes, fixes the two planes. These two planes will be the path of the needle. So you see one snapshot, we call these snapshots, and he fixes the other snapshot, and he will try to insert the needle at the intersection of the snapshots. So the target is at the far side. So this video is actually 7 years old. So you can see that even 7 years ago, you could do, well, geez, almost 8. You could do many things with Slicer IGT. And of course, we have lots of new tools and nice visualizations. One relatively recent example that Steve also touched on is breast conserving surgery, which is a minimally invasive technique to cut out the cancerous mass from the breast. The problem was that if you cut too close to the edge of this mass, then you create a positive margin, as you can see in the picture, which means that some of the tumor is actually left in the patient. And by guidance, you can minimize the risk of this happening. And you can see a slicer IGT based application called LampNav in the operating room. So they are now with a touch interface, they are segmenting the tumor under ultrasound imaging with multiple planes. And this is how they are defining the plan during anesthesia and everything. And then once they have the segmentation of the plan, they insert the guide wire that keeps the tumor in a known location. You can see the guide wire here in this fluoroscope image. And under guidance, looking at two different views, they are doing the excision. And when you have positive margin, then there's a warning of sound and color change in the navigation view. And after you extracted the tumor, then this is the result. So of course, as I said, these are pretty complicated procedures, and training is needed. So to this end, another extension called PerTutor was built on top of Slicer IGT, the goal of which is to teach basic and advanced skills to use the ultrasound, to use navigation system, and to insert needles. And the advantage of using PerTutor, aside from providing the tools to build the phantoms in-house and to set up the scenarios, is that it can measure your performance. So in the past, typically the Halstead method was used for training. You see one, you do one, and teach one. This is the basic concept, but unfortunately, trainees don't progress at the same pace. So some people will grasp one concept fast and others slow, and the next one would be fast for the other group and slow for the first one. So one cannot really know, but we can measure it. So here comes competency-based medical education in the picture, which means that you give a score to the individual trainee on a certain session, and you can make sure that they reach competency before progressing to the next case. So the first example also many years ago was nephrostomy training, when you do the procedure with various levels of guidance. First, you see everything: the ribs, the kidney, and other structures that you want to see. You see the position of the tumor, you see the needle, you see everything. And then we gradually take away the information, and at the end, the trainee can be pretty confident of doing this with minimal or no navigation as well. Of course, there are procedures where it is not possible to do it without navigation, but we can tailor this training for the certain intervention. So for example, a central line tutor, if it's loaded, hopefully, yes. So this is a pretty complex intervention, as most of you know, and not because it is very hard to perform, but because it has many steps. So you can see in the video that here there's a list of steps, and there's a webcam here, a camera, the image of which you can see here, and everything is recorded. The ultrasound image, the ultrasound position, the video, everything is recorded and is used for evaluation. And as you see, the steps of the procedure are automatically recognized and populated by the system. So if the trainee skips a step, then they get a warning, and gradually, as they do it many times, they will learn what comes after what and how to do it exactly. And based on these measurements, we can give them a score how well they did during the training. So basically, a training system like this can be built for a wide range of different procedures. One larger topic in the slicer ecosystem is radiation therapy. I had the fortune of leading the Slicer RT project for half a decade. As you can see, the goal of it is to irradiate a tumor from different angles with very complex geometries, with huge machines. So it is a very complicated area, but we can provide some tools. So for example, this extension contains around 20 modules, and while some other extensions contain 1 or 2, depending on how much special features they needed. For example, in this case, we can do a workflow called image-guided radiation therapy, where we have so-called fractions, first day, second day, etc. We have to register the images, so bring them to the same frame of reference. we get the dose volumes that were deposited to the tumor, and on the same frame of reference, we can add the dosages together and see the total dose that was delivered. The advantage of this is that during the fractionation, we can decide if we are on the wrong track, and we can do replanning, and we can exactly measure what is the dosage that the tumor and the organs at risk have received. So we have more confidence in delivering the whole treatment. Other usages of this extension is to be able to plan irradiations for new techniques, for example, proton dose calculation, where the radiation is not completely passing the patient like with typical photon beams, but so-called stops. So you can do different kinds of treatments, and an experimental dose calculation and planning system was created in Slicer RT. Also, one of the first so-called slicelets, Steve also mentioned briefly this concept, is a slicelet or a guidelet is a simplified slicer that makes it much easier to learn and use. So in this picture, you can see that instead of the complex user interface, you can just have the steps one by one, and you can do analysis in a simple way. I don't want to go into the details of this, but you can see that a pretty complex procedure can be done by a linear guidance, so that it is much easier to digest to the user. Also, one of the major topics in slicer usage and research is DMRI, diffusion magnetic resonance imaging, loading and visualizing and quantifying certain things in the diffusion data. Diffusion data, if you don't know, is basically an imaging technique that measures the flow of water in the body and can predict the fiber tracts in the brain. So, for example, if you visualize the tracts, then starting from a certain point, then you can determine which brain functions would be damaged if you cut at that certain point, etc. And this extension and module set is providing support for this kind of work. Also, as Steve mentioned, there are very different kinds of extensions like Slicer Astro, where they measure hydrogen content of certain galaxies and parts of space. So there are lots of opportunities that can be explored using Slicer. So this is about extensions. Thanks again for your attention, and now it's again Steve's turn. Thank you.
Okay, thank you, Csaba. I am ready to now start talking about actual code. It's we've been through quite a bit of background, and I hope you'll appreciate why the background is very important for kind of motivating, you know, the specific choices that you have to make as a developer, and also hopefully now you've got an idea of what's possible, how far Slicer can be extended and modified. What I want to do now is walk you through a tutorial. Normally, this tutorial would be something that you might do in a large classroom setting where everybody follows along and does the steps, in which case it takes maybe even more than an hour to do. So we're going to go through very quickly, but I want to use it just to kind of illustrate the steps. And then what I would encourage everyone to do, everyone who's thinking about becoming a more serious developer, to go to the website. You'll find the link to this very easily, and you can get the data that's being used here, and you can run through this yourself. And I want to give credit to Sonia Pujol. She's a professor at the Brigham and Women's at Harvard Medical School, and she's for many years now been the director of training, and she is quite skilled at using Slicer and at training. She's trained at maybe at this point certainly dozens of countries around the world, and also at major medical conferences. So this is material that's freely made available to you, and hopefully you'll find it useful.
We will be having Sonia tomorrow.
Ah, great.
Yes.
Ah,
yes.
Well, I'm a pale imitation of Sonia, but I'll do my best.
You're handsome. She's pretty, you're handsome.
Okay, well, good. All right. Well, that's probably what sells Slicer then. We get the benefit of the doubt because of that. So anyway, the goal here is just to give you a sense. Now we're calling this Slicer 5 because we're we're nearly there to release Slicer 5. And so what you can download now from the Slicer website is Slicer 4.13 is the current prototype of Slicer 5, but probably within a month or so, it will be released as Slicer 5. So, okay, so the 3 parts of this tutorial are just to kind of give you the sense of what we're going to try and do, and then we'll start introducing you to Python in Slicer, and then we're going to talk about user interfaces in Slicer. So it's always very good to remind, I know there's going to be some repetition here, but that Slicer is free and available, but it's not FDA or CE mark approved. So use it for research, use it for whatever you feel comfortable using it for, but be sure to follow whatever regulations exist. So the materials, this is the link that I mentioned. This is where you can get it from Sonia's GitHub site. You can get the tutorial data as well as version 4.11 now, but as I mentioned, you can very soon get version 5. So we'll talk about modules. There are many, many modules in Slicer. And since we already talked about this, I'm going to go quickly through it. There are many types of modules. The CLI modules are written in C++, and they're really, if you're familiar with just the regular Unix command line executable, they really are just executables. They use main and standard in and standard out to communicate, and they're meant to be used in Slicer, but also in batch jobs and other purposes. There are also loadable modules, which are written in C++, but the third kind is what we'll focus on here, which are purely Python scripted modules. And when you use Slicer, you don't necessarily know which modules are implemented in which ways because they all expose a consistent user interface. Extensions we've talked about. Extensions in the end really are just collections of modules. And so, you know, that's just a grouping that we've chosen, but the module is kind of the fundamental concept. And we've talked about the App Store extension manager already. Okay, so the Python code that you're going to be working with, Slicer has internally got a Python interactor, and also it is its own instance of Python. That is, we compile a version of Slicer. So if you're familiar with Anaconda or you know, the Python executable that you might install in your operating system globally, those are completely independent of Slicer's Python. Slicer Python is internal to itself, and you have to install packages to it. And we do that because we want to have strict control over the compatibility between Slicer and its environment. So the libraries, we've mentioned some of these before. NumPy, people hopefully, if you're using Python for anything, you'll be familiar with NumPy, but some of these others are kind of exotic, let's say. VTK is for visualization, ITK for image analysis. CTK is a common toolkit that spans a number of different projects, Slicer being one of the founding members of the CTK consortium, but there are others from different universities and different projects in Europe. Python Qt is a binding between the Qt toolkit and Python. Qt is the graphical framework that's used quite extensively. It's a very nice toolkit, available open source, but it's C++, and so Python Qt gives us an ability to use it. So for Python programmers, you know, some of the critical things that you have at your disposal are the package index. So PyPy has 200,000 Python packages. Most of those are pure Python. Some of them are C++. The majority of them can be installed directly in Slicer using the pip utility. We provide a pip_install command, which is a customization just to get it into the Slicer Python. But things that you may be familiar with, like TensorFlow, SciPy, PyTorch, Pandas, they're all available. And also you can use Jupyter. Nowadays, huge amount of science publication and development is done using Jupyter. And it works quite nicely. So Slicer acts as a kernel. And you can also use the Python development tools like debuggers and other IDEs like PyCharm together with the Slicer environment. So now we're at Python version 3, VTK actually version 9. That's a typo in the slide, and ITK version 5. So these are the latest releases of these packages. And when you get into the Python console, you have direct access to all these tools. It's really quite powerful and takes quite a bit of time to learn, but at the same time, you can get started with what I think are some really useful things. So when you have Slicer running, there's a Python icon on the toolbar, which brings up this Python interactor down in the bottom of the screen. For this tutorial, one would start with 2 MRIs, 2 different contrasts, and they're very easy to load. So in this tutorial, you would load one using the user interface, drag and drop the T1 nerd file, and then you see it loaded on the screen. So that, just to quickly give you an idea, the kind of big picture is that it's open source software with lots of things you can do with it. Beneath the surface, and I'm going to say this and then Csaba's going to tell you a little bit more depth about it, the data model includes the scene description. I already told you about the MRML, and the scene is made up of these concepts called nodes. And a MRML node is the abstract type, and then there are special types for volumes, models, etc. So there are also different specialization for display nodes, which describe how something should be visualized, and storage nodes, which describe how something should be stored on disk and restored from disk. So one of the things that one will need to get comfortable with in working with Slicer is getting a feel for the distinction between these different types of nodes and understanding the relationships between them. You know, I have to say it's actually really nicely organized, but I can also understand it takes a while to learn how these pieces fit together. So one of the key concepts in a node is the idea of an ID. So every node in the scene has an ID, and every node can be visualized in the data module by showing the list. Normally every node has a name, which typically is unique, but it's not required to be unique, but the ID is required to be unique. So if you're ever dealing with the programming level and you want to refer to nodes or search for them or keep references to them, you have to work with the IDs. So in the interactor, what you can do is make use of some utilities. So when you're in the interactor down here, I think you can see down there in blue, it's the same that's inside the orange box. Basically, we're using the syntax, the Python syntax. So we're saying this variable n is going to be the node that is named T1. Now, getNode is a convenience utility that basically allows you to get nodes by name or ID. For interactive use, we often just search by the name because it's usually okay. But if you're writing a script, you want to be more specific than that. Now, as I mentioned, this node T1, it's a volume, but it has associated with it a display node. There's actually a little typo there. That should be a capital G. Sorry about that. So this variable ND is the display node associated with the volume node, and it has all kinds of operators on it that allow you to affect the way the node is displayed. And so in this case, we're turning off interpolation. And when you run that, I don't know if you can see super clearly, but the interpolation is now turned off, and this is now a sort of a pixelated version of the display. So you can turn interpolation back on just by using the opposite command. Now, all these commands you have to find out about somehow. There is documentation on the various pages, and we'll include some pointers to that later on. So accessing the voxel. So this is kind of the fundamental thing. We're talking about image processing a lot of the time. So the slicer.util package is a built-in thing that's part of the Slicer Python environment. And it includes some utilities for getting images as NumPy arrays that you can operate on and also modify. So let's look at some examples of that. So one of the things you can do with an array is you can print it. And so because slicer.util is built in, you have the option of either using it, in which we would encourage if you're writing a script, or you can use the shorthand when you're typing in the console, and you get access to this array A. And one of the things you can do is just print it. So printing A, what you see here is, if you're familiar with NumPy, the sort of abbreviated output form. But what these numbers are representing, you can see the three brackets. This is a triply nested array. So this array, this line, each one of these lines represents a row out of the image, and each collection here represents a slice. They're sort of collected within these double square brackets, and then all together within the triple square brackets is the three-dimensional volume, and those numbers correspond to the pixel values. And if this were a live version of Slicer, as I mouse over down in the lower left, you'd see the data probe would tell me the numbers, and they'd be the same numbers that show up in this array. Because it's a NumPy array, you can actually do convenient operations on it. So if you take that array A, you can ask for the min and the max of those. You can ask for quite a few things, mean, standard deviation, and so forth. And then you can do operations on those. You can print out the min and max values out of the set. I'm afraid that thing keeps popping up, but there you can see, I think down in the corner, it's kind of small, but 0 and 4095 are the min and the max values of this T1 image. Similarly, because it's a three-dimensional array representing a volume, you can ask for the shape, and what you see in the lower left is that the shape of this is 208 by 320 by 300, and that's there's the pixel size of this data. Similarly, you can modify the data, and for efficiency, well, just let's take this in two steps. The first step there says A, where A is less than 800 equals 0. And that's a very powerful operation. It's a NumPy built-in operation that allows you to select the subset of pixels within that giant array, and only the ones that are less than the value of 800 are going to get set to 0. And then what you can do is you can call this modified operation. We allow you to do lots of operations on the data without reflecting it on the screen, but when you've finished all your operations, you can request that it be rendered by calling this array from volume modified. And what happens here now, you see that all the darker sections have all been set to black, and Slicer shows the results of running that threshold. Now, another thing you can do with the programming interface is you can programmatically load volumes. So here now we're getting the T2 volume with a command that's part of the Slicer util package. And then here, what we're going to do is we're going to define now a function that uses that functionality to implement part of our operation. So we're going to pass in a threshold T, going to use that in the expression, then we're going to call the modified. And so when we do this, we'll run threshold now at 500. It's going to get the T2 value and apply the threshold and modify. So there's the basic building block. That's, in a lot of ways, Slicer programming in a nutshell. I think if people study that and feel confident that they understand what each of the pieces was I just showed, you'll end up understanding a lot about what needs to be done. Everything's just kind of a generalization of that in many ways. So you get Slicer was a way to access and modify complex data types. You can use standard Python packages, and it's those turn out to be really useful for doing the kind of research that Csaba was just telling us about. So I'm going to really quickly tell you also a little bit more about the QT, but I want to save time too for Csaba to dig in to another level on the architecture. So QT, we talked about, it's used for creating the widgets, the dialogues, the text entries, the sliders, pop-up menus, all this kind of stuff. And Python Qt lets you access it from Qt, from the Python environment. And that's an incredibly powerful combination. Allows you to create user interfaces on the fly, allows you to do sophisticated interfaces that are quite, familiar to a lot of the user community. So here's an example where we've written another function here, very much like the previous one we looked at, which toggles the display, and it uses some kind of clever syntax here. So this is the toggle operation in some sense. You can see this was the same kind of procedure we did before, but this operation says we're going to take the maximum value of A and subtract A from it. And that's a vector-wise operation. That's saying, and it uses some concepts out of NumPy called broadcasting, where it's now going to take this A.max, like we saw before, as a single number, but A is a three-dimensional array. But because in NumPy we're mixing those two in the same line, we're actually going to have the result that this gets copied out to the full three-dimensional array, and then this operator is now going to assign that into the A contents. And that's a subtle thing. You're going to have to read up on that to maybe fully appreciate what I just said, but it's a very powerful thing. And unfortunately too, I guess the box isn't the right size, but then of course we call our modified event at the end as well. And now here's the trick, is we're going to connect that to a Q push button, right? So what we're going to do is we're going to create a push button called toggle. We're going to assign it to the variable B, and then this is an operation that connects the clicked signal from that button to our function toggle, which we just described in the last slide. So that's a key concept there. That's a signal and slot being connected to a widget. And then here, what we're also going to do is we're going to change the style of that. By default, Slicer uses its default style, which is either light or dark. But here we're going to assign special properties. We're going to make the color of the button aqua, and we're going to give it a different margin. Now, if you've ever done any HTML programming or web programming, you might be familiar with CSS, the cascading style sheet format, and that's what's going on here. And then we're going to call this show, which tells the button to show itself. And you can see that this has all been typed in down in the console in the bottom. And what happens is when you call show, you get this aqua colored push button with its special margin property. And then what happens is you can actually use that to toggle the values of the image. So you can click that as many times as you want. So that's a whirlwind tour, I know, but I think if you go through that tutorial yourself with your own version of Slicer, it should be compatible with any laptop or computer. You'll see how all the pieces fit together, hopefully, and then that'll give you a much clearer insight into a lot of the use of Slicer. And in fact, then you'll also find many, many good examples in the script repository of common things you might want to do, hopefully eye-opening in terms of things that you can map onto your actual research and development. So Slicer enables you to do a lot, and I think we've said all these things, so I'll skip the conclusion and pass it back to Csaba.
Thank you, Steve. I hope that nobody got disencouraged from all these complex things, but you will see that there's a ton of material online about how to do things. And as Steve said, if you do it on your own, then many things will clear up automatically. And as you try more and more things, and as you get your answers on this course, we also mentioned the Slicer forum. If you have a question, you do a search. There's a good chance that somebody already asked that question in the last 4 years. And if you can't find it, you can ask. And most likely my colleague András will answer you, or one of us, but you will get an answer in a pretty good time. So don't get discouraged. We are here to help. So after this great overview about the Python console and NumPy and Qt and all the things that you can do in the console, I would like to talk a bit about the internals of a module. So as I said, a module is a self-contained slicer building block that has a user interface on the left, and then it can do things into the internals of slicer and your data. So this is just an overview slide that we will get to the end at the end of what we want to achieve with a module. So, or with how it looks in slicer. So we have slicer application core that contains the murmur scene. This is where everything happens. So whatever is not in the murmur scene, it doesn't exist basically. So there is your image data, your registration transforms, your models, your user interface selections, everything is stored in the murmur scene. And this is why when you save the slicer scene and you load it back, you should see the exact same thing with the display, the angles of the camera, etc. So these modules are interacting with the murmur scene. These modules can be your own module on your hard drive. These can be slicer core modules. And of course, there are bundles of modules that you have in the downloaded extensions. And all of these modules and the slicer core uses this really robust and large set of libraries that are underneath slicer. Again, pretty vast API, I should say, but don't get discouraged. So we have Qt, which is, as Steve mentioned, is the 2D user interface library. We have the visualization toolkit. We have the ITK for image processing, CTK for medical-related widgets and DICOM, and we have some other. The list would actually go off the screen. So the data model, as we mentioned several times, and I'm pretty sure it's a little bit fuzzy in your minds still, but it is the so-called murmur scene, medical reality markup language. So it's a description of what you have in the application at a given time, and it contains a list of murmur nodes. So each node is an object that encapsulates some kind of information. It can be information like image data, as I said, or model, or it can be a set of UI selections, or it can be some display setting, again, like the camera, or the color of a volume, as you would see in the two-dimensional slice views, etc. And each of these nodes has an identifier. So, for example, these have a crosshair, which is a point of interest in the application. It has its own node type, crosshair node. We have selection node, we have the slice nodes, etc. And I wonder if there's any data node here. Well, let's say that the transform is a data. So as you say, we have very different types of nodes, and the modules, when slicer runs multiple modules, which usually happens, they don't communicate with each other directly. They communicate through the murmur nodes. So one module modifies a murmur node, and the other module can be notified about that. But the modules don't know about each other. They just know that, oops, this thing in the murmur scene that I'm interested in changed. So I should look at it, see how it changed, and do the thing that I need to do based on that. So what does a murmur node do? So it stores data, like image or transform. It can write itself to disk, and it can load itself back. But it doesn't do anything on its data. It just stores and it supports reading and writing. Actually, there are storage nodes to tell how they are going to be written to disk, but let's not go into these depths yet. So the basic types are the data nodes, the display nodes, so they are visualization options, and as I just said, the storage nodes that tell you how to write something to disk. So when you decided what kind of nodes you will want to interact on, then you have and how you want to interact with them. and you have a pretty good idea what your module should look like, then it's time to start implementing it. So what it looks like is that there are 3 classes. I think it would be redundant to explain what a class is, but if you're not sure, then please read upon it online in some tutorial or documentation, because this is a very basic concept in slicer programming. So we have 3 basic classes of each module. We have the module class itself that says, hey, slicer, this is me. I am my first module, and please know that I am here. So it doesn't, and I am created by these and these people, etc. Then in most of the cases, it has a widget class. No, sorry, logic is most of the cases. We always have a widget class that says this is how the module panel should look like. So it describes the buttons, the selectors, the text boxes, and everything that you can see and interact with in Slicer. And we most of the time have a logic class which actually does the operation on the data. So for example, if we made a module of the programming example that Steve just showed, then the logic class, for example, would contain the functions for the thresholding, like the masking the volume with the intensity values. So as I said, the module class is required, and this is how you can access it from the interactor. When I say interactor, it's the Python window that you could see. So you say slicer.modules. What is the name of your module, and then from here you can get the other two. So you can get the widget representation, and then you can get the logic. Of course, well, not of course, but unfortunately, there is a little difference between C++ and Python. So in C++, you can, or in case of C++ modules, you can get the logic like this directly from the module. But in Python, the logic class is not mandatory, but is created by the widget. So this is how you can get the logic for Python-based modules. But in general, if you just develop your own module on top of Slicer, you usually don't have to worry about any C++ details, which is more complicated and more. Sorry, I just want to see what is in the chat. Maybe it's relevant, but I can't find it. Anyway, if somebody has anything to say, please tell me.
Oh no, that was just Tagwa sent her compliments, so I was thanking her. Tagwa is our colleague from MGH, originally from Darfur, who's I think invited some more of her colleagues on here as well. So
okay, now it popped up. I don't know why I didn't.
Glad she enjoyed it.
Me too. All right. So let's go a little bit further with these. Sorry, with these architectural details. So the module creates the widget class, and the widget creates the logic class for Python modules. So the widget class defines the user interface. So in case of, for example, the volumes module, it tells you that you will have an active volume selector, you will have a section for volume information, and everything that you can see here. And the widget class is also responsible for changing some properties in the murmur nodes. For example, display nodes or anything that you can set from the user interface. And also when a murmur node changes, then the widget class gets notified and changes the selection. So for example, if I check the interpolate checkbox here, then the interpolation is turned on on the display node. So the image that you will see on the slice, in the slice view, will be smooth. But then if in the Python interactor you type interpolation off, as I remember you could see in Steve's example, then besides interpolation being turned off, actually on the view, this checkbox is turned off here so that they are in sync. And of course, the widget class starts operations on the logic. So for example, if you have an apply button and you click it, then it calls whatever operation is needed in the logic. So usually there is a murmur node specially for each module that stores the state of the module. So when you have a selection, then the parameter node knows that it is what is the selection. So if in the volumes module I have selected my MR and not my CT, then and I save the scene, then the parameter node is saved with the scene, and when you load it back, then the MR will be selected, not the CT, because we know from the parameter node what is selected. So this is almost the full picture of a module architecture in Python. So you have your module description class, you have your widget for the user interface part, you have the logic for the algorithmic and processing part, and you have murmur nodes that the widget class modifies and gets notified if they are changed and perform some operation if needed. So as I said, logic class is mostly needed because most modules actually do something, not just there to play with it. So the advantage of having logic class is that it encapsulates the non-user interface related operations of a module. So what does it mean? It means that you may not need to have the widget class if you want to just do the operations. So you can just instantiate the logic class and use it from Python as it was some library. And of course, the logic class may also serve the nodes. So, for example, if we are smoothing a model and the model is has changed, then the logic class can be notified and it can smooth the changed or the smooth the changed model, yes, to show as the output. A few things that we are not supposed to do, but sometimes people still do, is to use the widget from the logic. It's not recommended because we can achieve the same thing through murmur node observation. So if you feel the need to do something that we say is not good practice, then there's a good chance that it's because you're not using the murmur scene and the murmur nodes as intended. The reason that there are recommended ways of doing things is to keep the modules and your code easier to maintain, easier to read, so harder to make mistakes, harder to introduce bugs. So by good programming practices, you can actually reduce future work, and this is why it's good to follow them. So this green area is what you actually need for the logic processing, the batch processing, and the rest is if you actually want to use your module from Slicer user interface. So how do modules communicate? Not directly. They communicate through the murmur nodes. So if the logic of a murmur node if the logic of a module, modifies a murmur node, then the widget of the other module may get modified and do something in the logic. So it's always the murmur nodes through which the communication happens. Steve already introduced the Python console. One thing that may be worth mentioning is that you have autocomplete. So if you start typing some command, you get a little drop down and you can select the proper function that you want to use, and you can use the help. Steve also covered this. Yes, if you want to show the content of some variable, you can say print v, and then every node and every object has a print function that is used to print itself out. So you may get half a page, 1 page, or 10 pages of information based on what what object this is. And if you want to know what a certain function does, for example, get first node by class, you can just say help and then slicer.murmurscene.get first node by class, and then you will get the user, the developer documentation inside your Python window about what it does, what kind of parameters it has, and what value it returns. Of course, you can get the same information online from the documentation, but sometimes it's pretty useful to get it through here. Yes, you can do all kinds of manipulations. Actually, this is pretty useful. This is the overview of all the classes that you have in Slicer. So for example, display nodes and anything. And as a very last piece of information that I'd like to give you, because I know that we are mostly interested in image-guided therapy in this project, is that besides C++ and Python, we will need to use XML files, so-called configuration files for the Slicer IGT system description, so that you tell the application what kind of hardware you have, what connectors are plugged in where, what are the identifiers of the markers, what is the image size, whatever you need to change. So for example, in this file, you say that you have a Ascension 3D tracker, you have two tools, a reference and a stylus. You say that your ultrasound is a Sonics. The ultrasound image orientation is UF. You have some IP addresses, etc. And then you say that, okay, I want to mix these two devices into the same mixed device that contains not just the tracking, but also the image together, so that they form a whole information bundle that can be used in Slicer. So I know this was a lot, but thank you for your attention. You can see the slides online if you would like to read them again. You can check out the documentation and ask us on the forum. It was an honor being asked to participate in this session, and thank you very much.
Okay, thank you, Saba, and also thank you, Steve. If any of the participants have any questions, they are under, can send them to me by email, and I will transfer the questions for you. Thank you again. Thank you very much for your time and for sharing your knowledge with us.
No problem. Thank you, guys.
Welcome.
Bye.
Okay, goodbye.